In the second part of the lecture on electricity, I will discuss the electric force between two charges or two charged objects. Simple observations of the attraction or repulsion of two charged objects indicate that the size of the electric force depends on distance. For instance, a charged object has more effect on another object that is also charged when it gets nearer than when it's further away. But we need to be more precise. How does the size of the force vary as the separation between the two charged objects changes? And also, how does the electric force vary as the amount of charge on the objects varies? These questions were answered in 1785 by the French physicist Charles Coulomb, who measured the charges in the electric force as he varied the distance between the two objects and the charges on them. Coulomb verified that if the distance between two charged objects is doubled without changing the charges, the electric force on each object is reduced to 1/4 the initial value. If the distance is tripled, the force is reduced to 1/9, and so on. So this type of behavior is known as an inverse square relationship. So the electric force exhibits an inverse square relationship. This simply means that if the distance between the two charged objects is reduced, the force increases as the square of the distance between the two objects. And of course, if the distance between the two charged objects is increased, then the force decreases as the square of the distance between the two objects. Coulomb also showed that reducing the charge on one of the objects by 1/2 required or reduced the electric force to 1/2 its original value. Reducing the charge on each by 1/2 reduced the force to 1/4 the original value. So that means that the force is proportional to the product of the two charges. So the electric force is proportional to the product of the two charges. And so, combining those two observations, after some experimentation, Coulomb came up with the following formula for calculating the electric force between two charged objects. The electric force F between two charged objects is equal to the product of a constant K, the charge on the first charged object, the charge of the second charged object, divided by the distance between the objects to the second power. Here, the constant K has a value of 9 times 10 to the 9th Newton meter squared per Coulomb squared, and it's called the electric constant. Q1 is the charge of object number 1, or simply charge 1. Q2 is the charge of object number 2, or simply charge 2. And R is the distance between the two charges. Keep in mind that since in this formula we take the product of the two charges, it doesn't matter which charge is called Q1 and which charge is called Q2. The final result is still the same. Now let's sketch the situation, the system of two charges or charged objects, object number 1 with charge Q1 and object number 2 with charge Q2. The two objects are a distance r from each other. Now the question is, how is the force between the two charges, the electric force between the two charges, directed in this system of two charges? The answer is that it depends on the types of charges, whether these will be both the same or opposite charges. So let's first start with the two charges being the same. So the two charges Q1 and Q2 are the same. Either both are positive or both are negative charges. So then, since we know that like charges repel, the electric force will point away from the opposite charge or from the opposing charge. The question is this force the same for either charge? And the answer is yes, it is. This force is the same by magnitude for either charge because to calculate it we use the product of the two charges. So the force is not separated here or here by how much charge there is on each of the objects. It is the same for both. Now notice also that the force is directed along the line that connects the center of these two objects. So because of that, this is also known as a central force. Now let's see what the force direction is when the two charges are opposite. So here we have, again, the two charged objects with charges Q1 and Q2. But now the two charges are opposite. They're either positive and negative or negative and positive. But we know that opposite charges attract, so that means that the electric force will point towards the opposing charge here in this system. Again, since the force is calculated as the product of the two charges, that means that each of the charges experiences the same force. Again, notice that the force is directed along the line that connects the centers of those two charged objects. So, the formula for calculating the electric force depends as the 1 divided by the distance between the two charges to the second power. So that means that if we have those two charges here and here, and we bring them closer together, then the denominator here gets smaller, which means that the force will increase. And the force increases as the square of the distance between the two charges. If we move the charges further apart from each other, then the denominator here will increase, which then means that the force is reduced. And the amount by which the force is reduced is proportional to the square of the distance between the two charges. Let's do the following example using the definition of the electric force. By what distance must two charges, one of positive 3 coulombs and the other one of positive 9 coulombs, be separated so that the force between them is 5.2 times 10 to the 10th newtons? So let's first make a list of the information that's provided in the problem. So the first charge has magnitude of 3 coulombs and the second charge has magnitude of 9 coulombs. The force between the two charges is 5.2 times 10 to the 10th newtons, and the electric constant is not provided in the statement of the problem, but we know the value of it. That's 9 times 10 to the 9th newtons meter squared per coulomb squared. What we are looking for is the distance between the two charges. So we are going to use the definition of the electric force. The formula is that the electric force is equal to the product of the electric constant, charge 1, charge 2, divided by the distance between the charges to the second power. Since I'm looking for the distance between the charges, that means that I must rearrange the terms in this formula to find an expression for the distance between the two charges. So from here, r squared is equal to k q1 q2 divided by f, and from here my expression for the distance between the charges is square root of k times q1 times q2 divided by f. Let's plug in the numbers in this formula, and so we get square root of 9 times 10 to the 9th newtons meter squared per coulomb squared times 3 coulombs times 9 coulombs divided by 5.2 times 10 to the 10th newtons. So newtons here and here cancel out. The coulombs square here cancel with the coulombs here and here. And the final result is that the distance between the two charges is 2.2 meters. Let's do one more example. The nucleus of a certain atom contains 5 protons and 4 neutrons. When 3 electrons are removed from the neutral atom, the remaining 2 electrons have an average distance from the nucleus of 0.2 nanometers. What is the force between the nucleus and the remaining electrons? To find the answer to this question, again, we need to use the definition of electric force. Again, this is the product of the electric constant, the charge of the protons times the charge of the electrons divided by the distance between the electrons and the protons. The electric constant has a value of 9 times 10 to the 9th Newton meter squared per Coulomb squared. And now we need to find what's the amount of charge for the 5 protons and the 2 electrons. The charge of the 5 protons will be simply 5 times the charge of a single proton. So 5 times 1.6 times 10 to the negative 19 coulombs gives us 8 times 10 to the negative 19 coulombs. To calculate the charge of the electrons, simply multiply the number of electrons 2 by the charge of a single electron. Again, 1.6 times 10 to the negative 19 coulombs. And so this is equal to 3.2 times 10 to the negative 19 coulombs. Now we can substitute all of these values in the formula for the electric force. And so here we get 9 times 10 to the 9th Newtons meters squared per Coulomb squared times 8 times 10 to the negative 19 coulombs times 3.2 times 10 to the negative 19 coulombs. And then we divide this by the distance between the electrons and the protons. The distance between the electrons and the protons is 0.2 nanometers. However, to be able to calculate the electric force correctly, we need to replace the prefix nano with its power of 10 expression. So nano is equal to 10 to the negative 9th power. And so 2 nanometers becomes 0.2 nanometers becomes 0.2 times 10 to the negative 9th meters. And we need to raise this to the second power. So calculating all of that gives us that the force between the electrons and the protons is 5.78 times 10 to the negative 8 newtons.